Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss dumping or weeping through tray decks inside the fractionation tower. A distillation tray works efficiently when the vapor and liquid come into intimate contact on the tray deck. To this end, the liquid should flow evenly across the tray deck. The vapor should bubble up evenly through the perforations on the tray deck. The purpose of the outlet weir is to accomplish both these objectives as follows. 1. Uneven liquid flow across the tray deck is particularly detrimental to good vapor-liquid mixing. For example, if half of the tray deck has stagnant liquid, then the vapor bubbling through the stagnant liquid cannot alter its composition. Let me explain. A tray deck is a flat plate with holes. Liquid runs across the plate. Vapor bubbles up through the holes. If liquid only runs across part of this plate, vapor will still bubble up through the holes in the whole plate. The vapor bubbling up through that portion of the tray deck where the liquid flow is active will mix with the flowing liquid. The flowing liquid will wash out the heavier components from the rising vapors. On the other hand, the vapor bubbling up through that portion of the tray deck where the liquid flow is zero will also mix with the stagnant liquid. But it's like trying to wash dirty clothes in dirty water. The stagnant liquid cannot wash out the heavier components from the vapors, because it is already saturated with these heavier components. Uneven liquid flow is promoted by the outlet weir being out of level. Liquid will tend to flow across that portion of the tray with a lower than average weir height. The portion of the tray upstream of the high part of the outlet weir will contain stagnant liquid. However, if the crest height, that is, the height of picket weir liquid over the weir, is large compared to the out of levelness of the tray, then an even liquid flow across the tray will result. To achieve a reasonable crest height above the outlet weir, a weir loading of at least 2 GPM per inch of weir length is needed. When liquid flows are small, the tray designer employs a picket weir, as shown in this picture. 2. Uneven vapor flow bubbling up through the tray deck will promote vapor-liquid channeling. This sort of channeling accounts for many trays that fail to fractionate up to expectations. To understand the cause of this channeling, we will have to quantify total tray pressure drop. Tray pressure drop. Total tray DP. This picture shows a simple sieve tray with a single hole. Why is it that the liquid flows over the 3-inch outlet weir, rather than simply draining down through the sieve hole? It is the force of the vapor, the velocity of the vapor passing through the sieve hole, that prevents the liquid from draining down the sieve hole. This is true whether we are dealing with a valve cap, extruded perforation, or a sieve hole. The valve cap does not act as a check valve to keep liquid on the tray. On the other hand, bubble caps or even the more ancient tunnel cap trays are different, in that they do not depend on the vapor flow to retain the liquid level on the tray deck. Dry tray pressure drop. For the force of the upflowing vapor to stop the liquid from leaking through the sieve hole shown in picture, the pressure drop of the vapor flowing through the hole has to equal the weight of liquid on the tray deck. The weight of liquid trying to force its way through the sieve hole is proportional to the depth of liquid on the tray deck. The pressure drop of the vapor as it accelerates through the sieve hole is increment P dry equals KdV divided by dL times Vg square, where increment P dry equals dry tray pressure drop in inches of clear liquid. dV equals density of vapor, pound per feet cube. dL equals density of liquid, pound per feet cube. Vg equals velocity of vapor or gas flowing through the sieve hole, feet per second. K equals an orifice coefficient, which can be as low as 0.3 for a smooth hole in a thick plate and 0.6 to 0.95 for various valve tray caps. Hydraulic tray pressure drop. The weight of liquid on a tray is created by the weir height plus the crest height. We have defined in previous video that the crest is height in inches of clear liquid. As crest height equals 0.4 GPM divided by inch outlet weir length, carat 0.67. The actual height of fluid overflowing the weir is quite a bit greater than we calculate with this formula. The reason is that the fluid overflowing the weir is not clear liquid, but aerated liquid, that is, foam. The fluid on the tray deck, below the top of the weir, is also foam. This reduces the effective weight of the liquid on the tray due to aeration. To summarize, the weight of liquid on the tray, called the hydraulic tray pressure drop, which is increment P, hydraulic, equals AF times WH plus 0.4 GPM divided by inch outlet weir length, caret 0.67. Where increment P, hydraulic, equals hydraulic tray pressure drop, in inches of clear liquid. WH equals weir height, in inches. AF equals aeration factor. GPM equals gallons, US, per minute. The aeration factor AF is the relative density of the foam to the density of the clear liquid. It is a combination of complex factors, but is typically 0.5. Calculated total tray pressure drop. The sum of the dry tray pressure drop plus the hydraulic tray pressure drop equals the total tray pressure drop. Increment P total equals increment P dry plus increment P hydraulic expressed in inches of clear liquid. When the dry tray pressure drop is significantly less than the hydraulic tray pressure drop, the tray will start to leak or weep and tray efficiency will be adversely affected. When the dry tray pressure drop is significantly greater than the hydraulic tray pressure drop, the liquid on the tray can blow off the tray deck and tray efficiency will be adversely affected. For a tray to function reasonably close to its best efficiency point, the dry tray pressure drop must be roughly equal, plus or minus 50%, to the hydraulic tray pressure drop. dP dry equals dP hydraulic. This concept is the basis for tray design for perforated tray decks. While various valve tray vendors maintain that this rule does not hold for their equipment, it is the industrial experience that valve trays leak just as badly as do sieve trays at low vapor hole velocities. To summarize, increment P total equals KdV divided by dLVG squared plus AF times WH plus 0.4 GPM per inch outlet weir length, caret 0.67. Other causes of tray inefficiency. Out of level trays. When trays weep, efficiency may not be significantly reduced. After all, the dripping liquid will still come into good contact with the upflowing vapor. But this statement would be valid only if the tray decks were absolutely level. And in the real world, especially in large, greater than 6 feet, diameter columns, there is no such thing as a level tray. In this picture, the edge view of a tray that is 2 inches out of level. As illustrated, liquid accumulates on the low side of this tray. Vapor, taking the path of least resistance, preferentially bubbles up through the high side of the tray deck. To prevent liquid from leaking through the low side of the tray, the dry tray pressure drop must equal or exceed the sum of the weight of the aerated liquid retained on the tray by the weir plus the crest height of liquid over the weir plus the 2-inch out of levelness of the tray deck. Once the weight of liquid on one portion, the lowest area of a tray deck exceeds the dry tray pressure drop, the hydraulic balance of the entire tray is ruined. Vapor flow through the low area of the tray deck ceases. The aeration of the liquid retained by the weir on the low area of the tray deck stops, and hence the hydraulic tray pressure drop increases even more. As shown in picture, the liquid now drains largely through the low area of the tray. The vapor flow bubbles mainly through the higher area of the tray deck. This phenomenon is termed vapor-liquid channeling. Channeling is the primary reason for reduced distillation tray efficiency, because the vapor and liquid no longer come into good, intimate contact. The common reason for out-of-levelness of trays is sagging of the tray decks. Sags are caused by pressure surges and sloppy installation. Sometimes the tray support rings might not be installed level, or the tower itself might be out of plumb, meaning the tower itself may not be truly vertical. Loss of downcomer seal. I told you in a previous video that the top edge of the outlet weir is maintained about 0.5 inch above the bottom edge of the inlet downcomer to prevent vapor from flowing up the downcomer. This is called a 0.5 inch positive downcomer seal. But for this seal to be effective, the liquid must overflow the weir. If all the liquid is weeping through the tray deck, there will be no flow over the weir, and the height of the weir will become irrelevant. This picture shows the result of severe tray deck leakage. 1. The downcomer seal is lost on tray deck 1. 2. Vapor flows up the downcomer between tray decks 1 and 2. 3. Liquid flow is backed up onto the tray above, onto tray deck 2. 4. The dry tray pressure drop through tray 2 decreases due to low vapor flow through the tray deck. 5. The hydraulic tray pressure drop on tray 2 increases due to increased liquid level. 6. Tray 2 will now start to weep, with the weeping concentrated on the low area of the tray. 7. Tray 2 now has most of its vapor feed flowing up through its outlet downcomer, rather than the tray deck, and most of its liquid flow is leaking through its tray deck. The net result of this unpleasant scenario is loss of both vapor-liquid contacting and tray efficiency. Note how the mechanical problems like levelness of tray 1 ruins the tray efficiency of both trays 1 and 2. Flooding at reduced vapor rates. Check this picture. If a tray deck is leaking so badly that none of the liquid is overflowing its weir, then the downcomer from the tray above will become unsealed. Then, due to vapor displacing the liquid in this downcomer, all the trays above the unsealed downcomer will flood. This gives rise to an unusual and rather confusing situation. That is, lower vapor rates, which cause a reduced dP through the trays, can cause flooding. Worse yet, the way one stops this flooding is to increase the dP across the sagging tray deck by increasing the vapor flow, for instance, by increasing the reboiler duty or stripping rate. This contradicts common sense that flooding is promoted by higher vapor rates. But we can stop flooding in a crude distillation tower in a refinery by increasing the stripping steam rate. Also, you can observe that increasing vapor rates in a column reduces tray dP. Bubble cap trays. The major advantage of a bubble cap tray is that the tray deck is leak-proof. As shown in this picture, the riser inside the cap is above the top of the outlet weir. This creates a mechanical seal on the tray deck, which prevents liquid weeping, regardless of the vapor flow. Bubble cap trays may be operated over a far wider range of vapor flows, without loss of tray efficiency. In this picture you can see a bubble cap showing vapor pathway in operation. Bubble cap trays fractionate better in commercial service than do perforated valve or sieve trays. Why, then, are bubble cap trays rarely used in a modern distillation tower? There really is no proper answer to this question. It is quite likely that the archaic, massively thick, bolted up, cast iron bubble cap or tunnel cap tray was the best tray ever built. However, compared to a modern valve tray, bubble cap trays were difficult to install because of their weight. Have about 15% less capacity because when vapor escapes from the slots on the bubble cap, it is moving in a horizontal direction. The vapor flow must turn 90 degrees. This change of direction promotes entrainment and, hence, jet flooding. They are more expensive to purchase. They are more difficult to clean. But in the natural gas fields, where modern design techniques have been slow to penetrate, bubble cap trays are still widely employed to dehydrate and sweeten natural gas in remote locations. Distillation tower turndown. The problem we have been discussing is loss of tray efficiency due to low vapor velocity, is commonly called turndown. It is the opposite of flooding, which is indicated by loss of tray efficiency at high vapor velocity. To discriminate between flooding and weeping trays, we measure the tower pressure drop. If the pressure drop per tray, expressed in inches of liquid, is more than 3 times the weir height, then the pore fractionation is due to flooding. If the pressure drop per tray is less than the height of the weir, then pore fractionation is due to weeping or dumping. One way to stop trays from leaking or weeping is to increase the reflux rate. If the reboiler is on automatic temperature control, increasing the reflux flow must result in increased reboiler duty. This will increase the vapor flow through the trays and the dry tray pressure drop. The higher dry tray pressure drop may then stop tray deck leakage. The net effect is that the higher reflux rate restores the tray efficiency. However, the largest operating cost for many process units is the energy supply to the reboilers. We should therefore avoid high reflux rates and try to achieve the best efficiency point for distillation tower trays at a minimum vapor flow. This is best done by designing and installing the tray decks and outlet weirs as level as possible. Damaged tray decks should not be reused unless they can be restored to their proper state of levelness, which is difficult if not impossible. New high-capacity trays. All vendors now market a high-capacity tray. These trays have a 5 to 15% capacity advantage over conventional trays. Basically, the idea behind these high-capacity trays is the same. The area underneath the downcomer is converted to bubble area. This increase in area devoted to vapor flow reduces the percent of jet flood. But what keeps vapor from blowing up the downcomer? What prevents loss of the downcomer seal? If the downcomer seal is lost, surely the downcomer will back up and flood the upper trays of the column. The design of this type of tray is the Norpro high-capacity tray shown in picture. The head loss through the orifice holes in the downcomer seal plate shown is sufficiently high to prevent loss of the downcomer seal. These trays flood rather easily when their designed downcomer liquid rates are exceeded. However, when operated at designed downcomer liquid rates, they perform very well indeed and have shown quite a high vapor handling capacity as compared to conventional trays. The downcomer seal plate shown in this picture is an example of a dynamic downcomer seal. The Koplichnaya tray also uses a dynamic downcomer seal to increase vapor handling capacity. All trays with a dynamic downcomer seal suffer from two disadvantages. Loss of flexibility in that the liquid rates cannot be varied over too great a range without either flooding or unsealing the downcomers. Tray installation complexity is always increased, sometimes with terrible consequences. For these reasons, high-capacity trays using dynamic downcomer seals are best avoided on new columns. They should be reserved for use on retrofit tower expansion projects. Calculating tray efficiency. The viewer with a chemical engineering background will observe that I've neglected the calculation of tray efficiency. There are three methods available to calculate tray efficiency: overall tray efficiency, Murphy tray efficiency, mass transfer tray efficiency. I've never had occasion to calculate tray efficiency for any distillation tower. I'm guided by observations on similar existing services. Certainly, tray hydraulics as described above, that is, levelness, weeping, entrainment, is the dominating factor in determining tray efficiency. However, when I run a computer simulation for a distillation column, and must then select a tray efficiency, I'm guided by the following. Absorption of ethane, propane 50%. Deethanizer, demethanizer 60%. Sour water stripper for H2S, NH3-50%. Debutanizer 80%. Crude distillation 90%. Amine regeneration 70%. FCU, coker fractionators 90%. Pump arounds 80%. Vacuum distillation hydrocarbons 70%. Steam stripping hydrocarbons 50%. I don't have a solid basis for any of the above parameters. The values quoted are mostly what I've seen other designers use. Large negative variations from these parameters are rarely due to any calculation problems. Almost always, the problem is bad tray design or sloppy installation, or both. The majority of the towers I work with have too many trays. Designing for extra trays is the designer's futile attempt to offset tray hydraulic problems described in this video. Tray inspection after installation or during a unit turnaround is a lot more important than the selection of the best tray efficiency calculation model. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.